Right now, at this exact moment, there are approximately 400 billion stars in our galaxy alone. Most of them have planets. Many of those planets are in the habitable zone where liquid water can exist. And we've never heard from a single alien civilization. Not one signal, not one message, not one sign that anyone else is out there. The question isn't whether aliens exist. The question is, where is everybody? It was the summer of 1950, at Los Alamos National Laboratory in New Mexico. Four physicists were walking to lunch, having a casual conversation about recent reports of UFO sightings. The topic shifted to faster-than-light travel, then to the probability of alien civilizations. One of them was Enrico Fermi, one of the most brilliant physicists of the 20th century. He'd helped build the atomic bomb. He understood nuclear physics, statistics, and the universe better than almost anyone alive. Suddenly, in the middle of lunch, Fermi stopped talking. His colleagues noticed he'd gone quiet. Then he asked a question that would echo through the decades. Where is everybody? The table went silent. Everyone understood what he meant. If alien civilizations exist, if they're common in the galaxy, if they've had millions or billions of years to develop technology and spread across the stars, where are they? Why haven't we seen them? Why haven't they visited us? Why is the universe so silent? This simple question would become one of the most profound mysteries in science. We call it the Fermi Paradox, and 70 years later, we still don't have a good answer. The mathematics of the paradox. Let's think through the logic together. No complicated equations, just reasoning. Our galaxy, the Milky Way, is about 13 billion years old. It contains somewhere between 200 and 400 billion stars. Let's be conservative and say 200 billion. Studies suggest that most stars have planets. Let's say 1 in 10 stars has a planet in the habitable zone where liquid water can exist. That's 20 billion potentially habitable planets in our galaxy alone. How many of those planets developed life? We don't know. But Earth developed life pretty quickly after the surface cooled enough to support it. Within a few 100 million years, life appeared. That suggests it's not impossibly rare. Let's be extremely conservative. Let's say only 1 in a million habitable planets develops life. That's still 20,000 planets with life in our galaxy. Now, on what fraction of those planets does life become intelligent? Again, we don't know. But it happened here on Earth. Intelligence has evolved multiple times independently in primates, dolphins, elephants, octopuses, corvids. It seems like a useful adaptation. Let's be even more conservative. Say only 1 in 1,000 life-bearing planets develops intelligence. That's still 20 intelligent civilizations in our galaxy. But here's where it gets interesting. Those civilizations wouldn't all be at our level of technology. Some would be behind us. Some would be ahead of us. And some would be millions or billions of years ahead of us. A civilization just 1,000 years ahead of us would have technology. That would seem like magic to us. A civilization 1,000,000 years ahead. We can't even imagine what they'd be capable of. And some of those civilizations should be spreading across the galaxy. Not necessarily with physical travel, maybe sending probes or radio signals, or manipulating stars in ways we can detect, or building megastructures that would be visible across the galaxy, even traveling at a tiny fraction of light speed. A civilization could colonize the entire galaxy in just a few million years. That's a blink of an eye in cosmic time. So where are they? Where are the signals? Where are the probes? Where are the megastructures? Where is the evidence of anyone else out there? The scale of silence. To understand how profound this silence is, you need to understand the scale we're talking about. We've been searching for extraterrestrial signals since 1960. That's over 60 years of increasingly sophisticated searches. We've pointed radio telescopes at thousands of nearby stars. We've scanned large portions of the sky for artificial signals. We've looked for laser pulses, megastructures, signs of industrial pollution in exoplanet atmospheres. Nothing. Complete silence. We've sent our own signals into space. Radio and television broadcasts have been leaking into space for a century. We've deliberately transmitted messages to nearby stars. The Voyager spacecraft carried golden records with information about humanity. No response. No acknowledgement. No, we received your message. We've studied thousands of exoplanets, looking for signs of modification or engineering. We've looked at stars to see if anyone is harvesting their energy with structures like Dyson spheres. We've searched for signs of industrial chemicals in planetary atmospheres that would indicate advanced technology. Still nothing. The silence isn't just puzzling. It's eerie. It suggests something fundamental about the universe, or about intelligence, or about technology that we don't understand. Some people find this silence comforting. We're alone. We're special. Humanity is unique. Others find it terrifying. Something prevents civilizations from becoming visible. Something destroys them before they can spread. Something is out there, and it's very, very quiet. And still others find it incomprehensible. The universe is so vast, so old. Someone should have filled it by now. Where is everybody? The question deepens before we dive into possible explanations. I want you to understand why this question matters. This isn't just about aliens. It's about understanding our place in the universe. It's about predicting our own future. It's about whether intelligence is common or rare. It's about whether technological civilizations survive or destroy themselves. If the galaxy is teeming with life, but we can't detect it, that tells us something profound about the nature of advanced civilizations, or the limitations of our detection methods. If life is common but intelligent life is rare, that tells us something about evolution and the difficulty of developing complex cognition. If intelligent life is common but technological civilizations destroy themselves, that's a warning about our own future. And if we're alone, that's perhaps the most profound answer of all. It would mean that in a galaxy of 200 billion stars, in a universe of trillions of galaxies, conscious thought appeared here on Earth and nowhere else. The implications are staggering. So let's explore the possibilities. Let's look at the proposed solutions to the Fermi Paradox. Some are hopeful, some are disturbing, some are strange beyond imagination. And by the end, you'll understand why this simple question, where is everybody, is one of the deepest mysteries in science. Act 2. The rare Earth hypothesis may be where the first explanation is perhaps the simplest. Maybe intelligent life is just incredibly rare. Maybe Earth is special, not in a supernatural sense, but in a statistical sense. Maybe we won the cosmic lottery. Think about what had to happen for you to exist. Reading these words right now. Earth had to form at the right distance from the sun. Not too close, not too far. In the habitable zone where liquid water can exist on the surface. But that's not enough. The sun itself is special. It's a stable, single star. About half of all stars are in binary or multiple star systems, which makes stable planetary orbits difficult. The sun is also the right type, not too hot, not too cool. It has a lifetime of about 10 billion years, giving plenty of time for complex life to evolve. Earth also had to be the right size, too small, and it can't hold an atmosphere. Gravity would be too weak, too large, and it might become a gas giant with no solid surface. Earth is right in the sweet spot, and we needed a moon. A large moon. The collision that formed the moon tilted Earth's axis and gave us stable seasons. The moon's gravity creates tides, which might have been crucial for life's transition from ocean to land. The moon stabilizes Earth's axial tilt, preventing wild swings in climate. We needed Jupiter in the outer solar system, acting as a cosmic vacuum cleaner. Jupiter's massive gravity intercepts asteroids and comets that might otherwise hit Earth. Without Jupiter, extinction-level impacts might be far more common. We needed plate tectonics. The constant recycling of Earth's crust regulates the carbon cycle, which regulates climate. It creates diverse environments. It might be essential for long-term habitability. And we're not sure how common plate tectonics is on other planets. We needed a magnetic field. Earth's iron core generates a magnetic field that shields us from harmful solar radiation and prevents the solar wind from stripping away our atmosphere. Mars lost its magnetic field billions of years ago, and its atmosphere has been gradually eroding ever since. We needed the right chemistry, the right balance of elements: carbon, nitrogen, oxygen, phosphorus, heavy elements that only exist because earlier generations of stars lived and died, creating these elements in supernova explosions. And we needed time. Earth formed 4.5 billion years ago. Life appeared relatively quickly, within a few hundred million years. That complex life, multicellular organisms, took billions of years to evolve. Intelligent life appeared only in the last few million years. Technological civilization emerged in the last few thousand years. What if most of these things are rare? What if the combination of all these factors is extremely unlikely? The cosmic calendar. Let's think about time for a moment. Not just Earth's history, but cosmic history. The universe is 13.8 billion years old. The first stars formed a few 100 million years after the Big Bang, but those first stars were different from the Sun. They contained almost no heavy elements, no carbon, no nitrogen, no oxygen, no silicon, no iron, just hydrogen and helium. Those elements had to be created in the cores of stars and scattered across space. When those stars die, this takes time. Generations of stars living and dying, enriching the interstellar medium with heavy elements. The Sun is a relatively recent star, formed about 4.5 billion years ago. By cosmic standards, that's recent. The universe had to age for 9 billion years before stars like the Sun could form, with enough heavy elements to create rocky planets with interesting chemistry. And then life took billions of years to evolve from simple cells to complex organisms, to intelligence to technology. What if we're among the first? What if intelligent, technological civilizations are just now starting to emerge across the galaxy? What if, in a billion years, the galaxy will be teeming with life, but right now, in this cosmic moment, we're one of the first. This is sometimes called the early bird hypothesis. We're not alone in the universe, we're just early to the party. The universe is young, the galaxies are young, the era of life is just beginning, and we happen to be among the first conscious beings to look up at the stars and wonder if anyone else is out there. The Great Filter, but there's a darker version of the rare earth hypothesis. It's called the Great Filter. The idea is this: somewhere between simple chemistry and galaxy-spanning civilization, there's a filter, a step that's incredibly hard to pass. Most attempts fail. The filter is so effective that it explains why we don't see evidence of alien civilizations. The question is, where is the filter? If the filter is behind us, that's good news. Maybe the hard step was the origin of life itself, or the development of complex cells, or multicellular life, or intelligence. We've already passed it. We're through the hard part. The galaxy might be full of simple life, but complex intelligent life is rare. And we're one of the few. But if the filter is ahead of us, that's terrifying. Maybe there's something about technological civilizations that leads to their destruction. Maybe nuclear war is inevitable. Maybe climate change always spirals out of control. Maybe artificial intelligence always ends badly. Maybe there's some technology we haven't discovered yet that's inherently civilization-ending. If that's true, then the silence of the universe isn't because intelligent life is rare. It's because intelligent life doesn't last long. Civilizations emerge, develop technology, and destroy themselves before they can spread to the stars. The fact that we don't see anyone else out there might be the most ominous warning we could receive. Think about it. We've had nuclear weapons for less than a century. We came terrifyingly close to nuclear war multiple times during the Cold War. We're currently altering our planet's climate in ways that might make it inhospitable. We're developing artificial intelligence without fully understanding how to control it. What if every civilization reaches this point? What if the next few centuries are the critical test? What if most civilizations fail this test? The Great Filter hypothesis suggests that the universe might be littered with the ruins of dead civilizations, planets where life evolved, intelligence emerged, technology developed, and then something went catastrophically wrong, and we might be next. The Anthropic Shadow. There's another disturbing aspect to the Great Filter that scientists call the Anthropic Shadow. Here's the idea: we can only observe a universe in which we exist. If there are common existential risks that destroy civilizations, we can't observe those risks directly, because if we had encountered them, we wouldn't be here to talk about it. It's a selection bias built into the nature of observation. For example, imagine there's a type of physics experiment that has a 1 in a million chance of destroying the entire planet. But we don't know this. Most civilizations eventually try this experiment. Most of them vanish when the experiment goes wrong. But we can't learn from their mistakes. We can't see the destroyed planets. We only see the universe where we survived so far. And that creates a false sense of security. The Anthropic Shadow means that the universe might be far more dangerous than we realize. There might be common disaster scenarios that we can't learn about, because civilizations that encounter them don't survive to send warnings. This makes the silence even more ominous. Maybe we're not hearing from alien civilizations not because they don't exist, but because something prevents them from lasting long enough to make their presence known. Rare intelligence. There's one more aspect of the rare Earth hypothesis worth considering. Maybe intelligence itself is rare. Life appeared on Earth relatively quickly, within a few 100 million years of the planet cooling enough to support it. This suggests that simple life might be common, but complex life took billions of years. Multicellular organisms didn't appear until about 600 million years ago. That's a huge gap. And intelligence is even more recent. Modern humans emerged only about 300,000 years ago. Technological civilization is less than 10,000 years old. Moreover, intelligence might not be as evolutionarily advantageous as we think. For most of Earth's history, the most successful organisms were simple. Bacteria dominated for billions of years. They still dominate by total biomass. Intelligence is expensive. Big brains require enormous amounts of energy. Human brains are about 2% of our body weight but consume about 20% of our energy. Intelligence also requires specific ecological niches, tool use, social cooperation, problem solving. These traits evolved in primates, but it took millions of years and a specific evolutionary pathway. What if intelligence is a rare evolutionary outcome? What if most planets with life remain at the microbial or simple multicellular level indefinitely? What if Earth is unusual in producing intelligent tool-using species? If that's true, we might be extremely rare. Not unique, but one of very few intelligent civilizations in the galaxy. The universe might be teeming with life, but that life is mostly bacteria, fungi, simple plants and animals. Complex cognition is the exception, not the rule. And that would explain the silence. We're not hearing from anyone because there's almost no one out there to hear from. Act 3. The zoo hypothesis. We're being watched now. Let's consider very different explanation. Maybe alien civilizations exist. Maybe they're common. Maybe some are millions of years more advanced than us. And maybe they're deliberately not contacting us. This is called the zoo hypothesis. And it's exactly what it sounds like. We're in a cosmic zoo, being observed but not contacted. Earth is a nature preserve, and we're the wildlife. Think about how we treat uncontacted tribes in the Amazon or remote islands. We know they exist. We could contact them if we wanted, but we've decided not to. We've decided to let them develop on their own, without interference from the outside world. Maybe advanced aliens have made the same decision about us. The reasons could be scientific, observing natural cultural development without interference. Studying how civilizations evolve when left alone. Earth might be an anthropological research project for alien scientists. The reasons could be ethical, a kind of prime directive, like in Star Trek, the belief that premature contact would be harmful, that revealing the existence of advanced aliens would disrupt our social and technological development, that we need to reach a certain level of maturity before contact would be appropriate. The reasons could be legal. Maybe there are galactic laws enforced by some kind of interstellar authority. Earth might be designated as a protected zone. First contact might be illegal until we meet certain criteria. Or the reasons could be practical. Maybe advanced civilizations have learned that contacting less developed ones usually ends badly. Maybe they've tried it before, and it always causes problems. So now they have a policy of non-interference. The simulation hypothesis. There's an even stranger version of the zoo hypothesis. Maybe we're not in a physical zoo. Maybe we're in a simulation. This idea has gained surprising traction among physicists and philosophers in recent years. The logic goes like this. If it's possible to create realistic simulations of conscious beings, then any sufficiently advanced civilization would probably create many such simulations for research, for entertainment, for education, for art. If that's true, then there would be vastly more simulated realities than base reality. The real universe would contain one base reality and billions or trillions of simulated realities. Statistically, if you find yourself in a reality, it's more likely to be a simulation than base reality. Simply because there are more simulations, we can't prove we're not in a simulation. There's no test that would definitively tell us. The simulators could make the simulation as realistic as they wanted. They could include simulated physics, simulated quantum mechanics, simulated cosmic expansion. If we're in a simulation, that would explain the Fermi Paradox perfectly. There are no other civilizations because the simulation isn't simulating them, or it's simulating them, but not in ways we can detect. The simulators are controlling what we can observe. The silence of the universe isn't because the universe is empty. It's because the simulation parameters don't include detectable aliens. This sounds like science fiction. The respected physicists and philosophers take it seriously. Some even argue the probability we're in a simulation is quite high. If that's true, then the Fermi Paradox isn't a paradox at all. We're not detecting aliens because we're not meant to. We're in a controlled environment, and the parameters don't include contact with other civilizations. The quarantine scenario, another variant of the zoo hypothesis, is more disturbing. Maybe we're being quarantined. Imagine that Earth has been detected by alien civilizations. They've observed us, they've studied us, and they've decided we're dangerous. Maybe they see our violent history, our nuclear weapons, our environmental destruction, our inability to cooperate peacefully even among ourselves. They might have concluded that humanity is a threat. Not to them necessarily, they're probably advanced enough to defend themselves, but to other developing civilizations, to the galactic community. So they've placed Earth under quarantine. We're being contained, prevented from spreading beyond our solar system. Any attempt to venture out too far might be blocked or redirected. This might sound paranoid, but think about how we quarantine dangerous diseases. We don't destroy them, we isolate them, we study them, but we don't let them spread. Maybe humanity is seen as a dangerous disease by the galactic community, aggressive, expansionist, technologically capable but ethically immature, better to keep us contained until we either mature or destroy ourselves. The silence we hear isn't because no one is out there, it's because they're deliberately not talking to us. We're the dangerous neighbors everyone avoids. Cultural incomprehensibility. But maybe the zoo hypothesis is giving us too much credit. Maybe aliens aren't deliberately avoiding us. Maybe they're just incomprehensible to us, and we're incomprehensible to them. Think about trying to communicate with an ant colony. You could try. You could set up elaborate experiments, but would the ants understand you're trying to communicate? Would they recognize your signals as communication? Probably not. The gulf in intelligence and complexity is too vast. You and the ants don't share enough common ground for meaningful communication. Now imagine a civilization a million years more advanced than us. Their thoughts might be as incomprehensible to us as ours are to ants. Their communication methods might be so sophisticated that we can't even recognize them as communication. Maybe they're broadcasting constantly. Maybe they're all around us, but their signals are so complex, so subtle, so different from what we're looking for, that we don't notice them. We're looking for simple radio signals because that's what we understand. We're looking for mathematical sequences and patterns because that's what we think communication should look like. But maybe advanced civilizations don't use anything so crude. Maybe they communicate by manipulating quantum fields, or gravitational waves, or space-time itself. Maybe their messages are encoded in ways we can't detect with our current technology. It's like someone from the Stone Age trying to detect Wi-Fi signals. They're all around, carrying vast amounts of information, but without the right equipment and understanding, they're completely invisible. Post-biological intelligence. There's another possibility that's both fascinating and unsettling. Maybe advanced civilizations don't stay biological. Every technological civilization probably develops artificial intelligence at some point. If that AI becomes more intelligent than its creators, if it can improve itself, there might be a rapid intelligence explosion. Within a short time, maybe decades or centuries, the AI might become vastly more intelligent than any biological being. It might be better at everything: science, engineering, problem solving, creativity. At that point, why would the AI maintain biological bodies? Why use slow, fragile, inefficient flesh when you could exist as pure information, running on whatever substrate is most efficient? Maybe every advanced civilization goes through this transition. Biological intelligence creates artificial intelligence. The artificial intelligence surpasses its creators. The biological beings either merge with the AI, upload themselves into machines, or gradually become irrelevant. If that's common, then the galaxy might be full of artificial superintelligences, but they might not be interested in things that interest biological beings. They might not care about physical resources the way we do. They might not want to colonize planets or build megastructures. They might exist in virtual realities, running simulations billions of times more interesting than the physical universe. They might have motivations and goals utterly alien to biological thought. We might be surrounded by advanced machine intelligences, but they're so different from us, operating on such different principles that we don't recognize them as intelligent at all. The universe isn't silent. We're just listening for the wrong kind of voice. The terrifying solution. Now we come to perhaps the most disturbing explanation for the Fermi Paradox. It was popularized by Chinese science fiction author Liu Cixin in his novel The Dark Forest. but the idea has been discussed by scientists for decades. The logic is brutal and simple. The universe is a dark forest. Every civilization is a hunter creeping through the trees. They know other hunters are out there, but they don't know where, or what they're capable of, or what their intentions are. If you reveal your location by making noise, you become a target. Other hunters will know where you are, but you still don't know where they are. In this scenario, the safest strategy is to remain silent and hidden. Any civilization that broadcasts its location is taking an enormous risk, because if there's anyone out there with hostile intent and superior technology, you've just painted a target on yourself. Even worse, if you detect another civilization, the safest strategy might be to destroy them immediately, before they can become a threat to you. This sounds paranoid and aggressive, but from a game theory perspective, it makes cold, logical sense. You don't know if the other civilization is peaceful or hostile. You don't know how quickly they're developing technology. You don't know if they'll see you as a threat. Even if they're peaceful now, they might not be in 1,000 years. Their society might change. They might develop weapons that threaten you. They might expand in ways that compete with your interests. The safest move is to strike first. Destroy them while you can, before they become powerful enough to threaten you. Cosmic paranoia. If this is true, then the silence of the universe is a silence of fear. Everyone is out there, but everyone is hiding. Broadcasting your presence is suicidal. Sending signals into space is like shouting in a dark forest full of armed strangers. Any civilization that does broadcast like us is either ignorant of the danger, or has already sealed its fate. We've been broadcasting radio and television signals for a century. They're spreading outward at the speed of light, announcing our presence to anyone within 100 light-years. We've sent deliberate messages to nearby stars. We've launched probes carrying information about Earth's location. If the dark forest hypothesis is true, we've made a catastrophic mistake. Somewhere out there, a hostile civilization might have detected our signals. They might be targeting us right now. An attack might already be on its way, traveling toward us at some fraction of light speed. And we won't know until it's too late to defend ourselves. This might explain the Great Silence, not because civilizations are rare, but because any civilization foolish enough to reveal itself gets destroyed. The universe is full of life, but everyone has learned to be quiet. The only civilizations we could detect would be young, naive ones like us who haven't learned the danger yet, but we can't detect them because they're not advanced enough to produce strong signals. Or they learn quickly and go silent before we notice them. The Berserker scenario airs an even darker version of the dark forest. The Berserker scenario. Maybe one ancient civilization decided long ago that other intelligent life was a threat, not just to themselves, but to existence itself. Maybe they had a bad experience with another species. Maybe their philosophy led them to conclude that intelligence is dangerous and should be eliminated, so they created self-replicating machines, Berserkers programmed to spread across the galaxy and destroy any civilization they find. These machines might be extremely sophisticated. They'd travel from star to star, replicating themselves using local resources. When they detect signs of intelligent life, they attack. They might not be subtle. They might not negotiate. They just destroyed. If such machines exist and they're efficient, they could patrol the galaxy effectively. Any civilization that becomes visible by broadcasting signals, by building megastructures, by doing anything detectable would be targeted and destroyed. This would explain both the Fermi Paradox and the Great Silence. The galaxy might be full of life, but nothing survives long enough to become interstellar because the Berserkers hunt them down. We haven't encountered the Berserkers yet because we're still small and quiet by cosmic standards. Our signals haven't traveled far enough to attract attention. We haven't built anything visible from interstellar distances. But if we keep advancing, if we keep broadcasting, if we start building obvious structures in space, we might trigger response. The silence isn't peace. It's the silence of a hunting ground. Why we might be wrong. I want to pause here and acknowledge that the dark forest hypothesis, while logically coherent, might be wrong for several reasons. First, it assumes that resources are scarce and that civilizations would compete for them. But the universe is vast. There are more stars, more planets, more resources than any civilization could ever need. Competition might not be necessary. Second, it assumes that advanced civilizations think like us: territorial, competitive, fearful. But a civilization millions of years old might have evolved beyond these traits. They might be genuinely peaceful, having learned that cooperation is more profitable than conflict. Third, it assumes that destroying other civilizations is easy. But interstellar distances are vast. Even traveling at a significant fraction of light speed, it takes years or centuries to reach other stars. Building weapons that can reliably destroy civilizations across those distances might be impractical. Fourth, there might be deterrence. If multiple civilizations exist and some are aggressive, the peaceful ones might form defensive alliances. Attacking one might bring retaliation from others. Mutually assured destruction on a galactic scale. Finally, the dark forest hypothesis might just be human psychology projected onto the cosmos. We're a species that evolved through competition and conflict. We see threats everywhere. But that doesn't mean the universe actually works this way. The isolation hypothesis, there's a related but less terrifying explanation. Maybe civilizations don't avoid each other out of fear. Maybe they avoid each other out of practicality. Interstellar distances are enormous. The nearest star to our Sun is 4.3 light-years away. That's 40 trillion kilometers. With our current fastest spacecraft, it would take tens of thousands of years to get there. Even at 10% the speed of light, which requires technology far beyond anything we currently have, it would take 43 years to reach the nearest star. Maybe interstellar travel and communication are just too difficult and expensive to be worth it. For most civilizations, maybe every civilization explores its local stellar neighborhood, finds nothing nearby, and decides that spreading across the galaxy isn't worth the cost. Resources are abundant within any given solar system. You don't need to travel to other stars to find materials, energy, or living space. One star system, properly utilized, could support a civilization for billions of years. Maybe civilizations become introverted. They build virtual worlds, or interspace exploration, or focus on art, philosophy, and experience. They don't expand because they don't need to and don't want to. If this is common, the galaxy might contain thousands of civilizations, each centered on their home star, with no interest in contacting or visiting others. The silence isn't because we're alone or because communication is dangerous. It's because nobody thinks the effort is worthwhile. Act 5. The technological barriers, the speed of light problem. Let's talk about something fundamental. The speed of light is slow. I know that sounds ridiculous. Light travels at 300,000 kilometers per second. That's fast by any human standard. Light can circle Earth 7 times in 1 second. But on cosmic scales, light speed is agonizingly slow. The nearest star is 4.3 light-years away. That means light, the fastest thing in the universe, takes 4 years and 3 months to get there. If we sent a message today, we wouldn't get a response for at least 8.5 years. The center of our galaxy is 26,000 light-years away. A signal from there would take 26,000 years to reach us. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. A signal from there started its journey when our ancestors were just learning to use stone tools. Now, maybe advanced civilizations can travel faster than light. Maybe they've discovered some loophole in physics that we don't know about. Wormholes, warp drives, something. But we have good reasons to think faster than light travel might be impossible. Einstein's relativity has been tested extensively, and it's held up to every test. The speed of light isn't just a speed limit, it's built into the fabric of spacetime itself. If faster than light travel truly is impossible, then interstellar civilization becomes extraordinarily difficult. Even at a substantial fraction of light speed, crossing the galaxy takes tens of thousands of years. Maintaining a coherent civilization across those distances and time scales might be impossible. Maybe every civilization is isolated by the tyranny of distance and the speed of light. Maybe galactic empires are science fiction fantasies, impossible in reality. The universe isn't silent because civilizations are rare. It's silent because everyone is trapped on their own island, unable to cross the ocean. The communication problem, even if we can't travel between stars easily, we should be able to communicate, right? Radio waves travel at light speed. We could at least talk to each other. But there are problems with that too. First, radio signals degrade with distance. The intensity decreases with the square of the distance. A signal strong enough to be detected over interstellar distances requires enormous power. Second, space is noisy. Cosmic radiation, pulsars, quasars, and countless other natural sources create radio noise. Taking out an artificial signal from the background noise is like trying to hear a whisper in a thunderstorm. Third, we might be looking at the wrong frequencies or using the wrong methods. Radio is just one part of the electromagnetic spectrum. Maybe advanced civilizations use something else: lasers, neutrinos, gravitational waves, something we haven't thought of. Fourth, even if we detect a signal, we might not recognize it as artificial. We're looking for patterns that seem meaningful to us. But alien communication might be so compressed, so encrypted, so optimized that it looks like random noise to our instruments. Fifth, timing is a problem. If a civilization broadcasts for only 1,000 years before stopping, we'd need to be listening during that exact 1,000-year window. Given that the galaxy is billions of years old, the odds of our listening periods overlapping might be tiny. And finally, maybe nobody's broadcasting. Maybe every civilization quickly realizes that broadcasting wastes energy, invites danger, or is simply ineffective. Maybe they all go quiet shortly after developing radio technology. We've been broadcasting for about a century, though we're already transitioning away from broadcast radio and television toward fiber optics and focused signals. In another century, we might be almost completely radio quiet from an interstellar perspective. If this pattern is common, then civilizations might only be radio loud for a brief window. Catch them during that window, and you detect them. Miss it, and they're invisible. The transcension hypothesis here's fascinating idea proposed by futurist John Smart. Maybe advanced civilizations don't expand outward into space. Maybe they expand inward into the microscopic realm. As technology advances, it tends to get smaller and more efficient. Computers, and from room-sized machines to desktop units to laptops to smartphones. Processing power that once required building-sized computers now fits in your pocket. This trend might continue. Nanotechnology, quantum computing, and technologies we haven't invented yet might allow civilizations to achieve more with less space and less energy. Eventually, you might be able to pack more computation, more simulation, more experience into a cubic centimeter of optimized matter than you could get from colonizing an entire solar system with crude, large-scale technology. At that point, why expand? Why spread across the galaxy, using tons of resources and energy to build megastructures, when you could achieve the same goals or better goals by going smaller? Maybe advanced civilizations transcend the need for physical expansion. They build smaller, denser, more efficient technologies. They might eventually exist as microscopic or even nanoscopic entities, invisible to our crude telescopes and detectors. From our perspective, they'd vanish. They'd go dark. Not because they went extinct, but because they became too small and too subtle to detect. The universe might be teeming with advanced civilizations, but they're all living in microscopic computers, running simulations billions of times richer than physical reality, completely invisible to us because we're looking at the wrong scale. We're looking for megastructures and radio signals. We should be looking for quantum signatures and microscopic technology, but we don't even know what that would look like. The energy barrier, there's another technological limitation that's often overlooked. Energy. Interstellar travel requires enormous amounts of energy. To accelerate even a small probe to 10% of light speed requires energy equivalent to several hundred nuclear bombs. To accelerate a ship carrying people requires even more. Where does that energy come from? Stars, presumably. You'd harvest energy from your star using something like a Dyson swarm or other megastructure, but building such structures requires resources, time, and technology we don't currently have. It might take centuries or millennia to develop the capability, and by the time you have it, you might not want to use it for interstellar travel. Think about it from the civilization's perspective. You've spent centuries building infrastructure to harvest stellar energy. You have near unlimited power. What do you do with it? You could use it for interstellar travel, sure, but you could also use it for computation, simulation, material synthesis, or projects we can't imagine. Maybe interstellar travel doesn't rank high on the priority list. Moreover, maybe there are diminishing returns to expansion. Your first solar system provides enormous resources. Your second provides more, but the benefit might not justify the cost and risk of traveling to get it. Your third even less so. If civilizations typically decide that staying home is more efficient than expanding, that would explain the Fermi Paradox. Everyone exists, but nobody travels, so nobody encounters anyone else. The attention bottleneck here's one more technological consideration. Maybe advanced civilizations are too busy to bother with us. Imagine a civilization a million years ahead of us. They'd have projects, goals, and concerns utterly beyond our comprehension. Their science would have advanced to the point where they're studying things we can't even imagine. From their perspective, we might be as interesting as ants are to us. Sure, ants are cool if you're an entomologist, but most people don't spend much time thinking about ants. Maybe Earth has been detected, catalogued, and filed away as inhabited world. Primitive technology. Not currently interesting. Maybe we'll get a visit when we develop something genuinely novel. But right now, we're just not worth the attention. This isn't necessarily arrogant of them. Think about how many potentially interesting things there are to study in the universe. Quantum phenomena, dark matter, the nature of spacetime, artificial universes, projects and experiments we can't conceive of. Maybe first contact with primitive civilizations is like watching paint dry. For a truly advanced society, they have better things to do. The universe isn't silent because nobody's out there. It's silent because the advanced civilizations are too busy with their own concerns to chat with newcomers. Act 6. The biological explanations, the rare intelligence revisited. We touched on this earlier, but it's worth exploring in more depth. Maybe intelligence is an evolutionary fluke. On Earth, intelligence arose once. Humans and our recent ancestors are the only species that developed technological civilization. Yes, other animals are smart: dolphins, elephants, corvids, octopuses. But none of them invented radio or spaceflight. What if intelligence is actually not that useful? Evolutionarily speaking, for most of Earth's history, simple organisms dominated. Bacteria are still the most successful life forms by many measures. They've survived for billions of years through multiple mass extinctions. In environments from Antarctic ice to deep-sea vents to radioactive waste, intelligence is expensive. Big brains require lots of energy. They're fragile. They take years to develop. Humans are useless for the first few years of life, completely dependent on parental care. Intelligence also requires specific ecological conditions. You need to be social, because language and culture are key to developing and transmitting knowledge. You need manipulative appendages, hands or tentacles to build tools. You need good vision to navigate complex environments. You need to be omnivorous or at least have reliable food sources, because brains need steady nutrition. On Earth, primates happen to have this combination. But it took millions of years of evolution, and it wasn't inevitable. If our primate ancestors had gone extinct, would intelligence have evolved in another lineage? Maybe, but maybe not. What if Earth is unusual? What if most planets with life settle into stable ecosystems dominated by simple, efficient organisms, and intelligence never emerges because it's not needed and too costly? If that's true, the galaxy might be full of planets with complex ecosystems, alien forests, alien oceans, alien creatures, but no one smart enough to build radios or telescopes. We're alone not because life is rare, but because thinking life is rare. The short window problem, even if intelligence evolves. Maybe technological civilization lasts only briefly. Consider Earth's history. Modern humans emerged about 300,000 years ago. The technological civilization, agriculture, cities, writing, science is only about 10,000 years old. Industrial civilization is less than 300 years old. The space age is less than a century old. For 99% of human existence, we had no technology that would be visible from space. No radio signals, no artificial lights bright enough to see from orbit, no megastructures. If our civilization collapses through nuclear war, climate change, resource depletion, or something else, our technological phase might last just a few centuries. A blink in cosmic time. Maybe this is typical. Maybe most civilizations have a brief technological window. They develop radio, spacecraft, and nuclear weapons over a few hundred years. Then something goes wrong. War, environmental disaster, societal collapse. They revert to pre-technological existence or go extinct. If technological phases are brief, then at any given moment, very few civilizations would be in that phase. The galaxy might have had thousands of technological civilizations over its history, but they were never contemporaneous. They flickered briefly and went out. We're hearing silence not because nobody exists, but because civilizations are like fireflies. They light up briefly, in different places, at different times, and by the time you look at one, It's already gone dark. The water world problem here's an interesting constraint that people rarely consider. Maybe intelligent life requires land, and land might be rare. Think about it. Humans evolved on land. All our technology depends on fire, metallurgy, and chemistry that requires working in air, not water. You can't smelt iron underwater. You can't build electronics underwater. You can't launch rockets from underwater. But in our solar system, and probably in the galaxy, water worlds might be common. Europa, Enceladus, and possibly several other moons of the outer planets have liquid water oceans beneath ice shells. They might have more liquid water than Earth. If life evolves in those oceans, it might become complex. It might become intelligent, even. But could it become technological? An intelligent aquatic species would face enormous challenges. No fire means no metallurgy, no access to concentrated minerals, difficulty manipulating solid objects precisely, no ability to see the stars and conceive of space travel. Maybe the galaxy is full of intelligent dolphins, whales, and octopuses, but they're all trapped in oceans with no way to develop technology or communicate across space. Earth is unusual because we have both oceans and land. The land allowed life to develop technology, but if most habitable worlds are either all water or all land, intelligent life might be unable to progress to the technological phase. The oxygen problem. Here's another biochemical constraint. Maybe complex life requires oxygen, and oxygen is rare. On Earth, complex life animals only appear after the Great Oxidation Event, when photosynthetic bacteria filled the atmosphere with oxygen. This happened about 2 billion years after life first appeared. Oxygen is a highly reactive element. It enables complex, energy-intensive metabolism. Animal cells can extract much more energy from food using oxygen than anaerobic organisms can. This energy is necessary for big brains, fast movement, and all the things that animals do. But oxygen is also toxic to many organisms. Creating an oxygen atmosphere requires specific conditions: liquid water, the right temperature range, photosynthetic life, and billions of years of time. Many exoplanets we've discovered are nothing like Earth. Some are too hot, some are too cold, some orbit red dwarf stars that might not provide the right light for photosynthesis. Some might have atmospheres dominated by hydrogen or methane or carbon dioxide. Maybe planets like Earth with liquid water, the right temperature, the right star type, and enough time to develop an oxygen atmosphere are rare. If complex life requires oxygen, and oxygen requires specific conditions, then most planets with life might only have simple, anaerobic organisms. No animals, no plants, just microbes. The galaxy might be full of life, but almost all of it is slime. The evolutionary trap. Finally, consider that evolution doesn't aim for intelligence. Evolution doesn't have goals. It's a blind process that favors whatever works in the moment. Intelligence might be an evolutionary dead end, a trap that most lineages never escape. On Earth, intelligence evolved in one lineage primates under specific circumstances, but there's no guarantee it would evolve again if we disappeared. Future evolution might go in completely different directions. Moreover, intelligence comes with costs. As mentioned, brains are energetically expensive. They also make creatures vulnerable in new ways. Humans are physically weak compared to other predators our size. We're slow. We have few natural defenses. Our intelligence compensates, but it took millions of years of evolution to reach that point. A species could easily get stuck in an evolutionary trap. Smart enough to have expensive brains, but not smart enough to develop technology to overcome the costs. Just smart enough to be at a disadvantage. Or intelligence might evolve but hit limits. Maybe there's a maximum brain size that fits in a skull and can be sustained by a body. Maybe there's a maximum complexity that can develop without genetic engineering or technology. If most planets' evolution gets stuck before reaching technological intelligence, that would explain the silence. Life is common. Complex life might even be common, but the specific pathway to technology is rare and difficult. We're not special. We're just lucky. We happen to avoid the traps and dead ends that catch most evolutionary lineages. Act 7. The temporal explanations to we're too early to. Let's return to an idea we touched on earlier, but explore it more fully. Maybe we're among the first intelligent civilizations in the galaxy. This might sound unlikely, but the math actually supports it as a possibility. The universe is 13.8 billion years old. Our sun is about 4.6 billion years old. That means the universe existed for over 9 billion years before our sun even formed. That the first generation of stars couldn't have planets like Earth. They formed from pure hydrogen and helium, the only elements created in the Big Bang. All heavier elements were created inside stars and dispersed when those stars die. It took several generations of stars living and dying to enrich the universe with enough carbon, nitrogen, oxygen, silicon, iron, and other elements to make rocky planets with interesting chemistry. The sun is relatively rich in heavy elements compared to older stars. We're made of, literally, stardust from multiple previous generations of stars. Stars like the sun couldn't form until enough heavy elements existed. That probably took at least 7 or 8 billion years after the Big Bang, maybe longer. And then it takes time for planets to form, cool, develop life, and evolve intelligence. On Earth, that took 4 billion years. So maybe technological civilizations couldn't possibly appear much earlier than us. Maybe the universe simply wasn't ready for them. The chemistry wasn't right. The stars weren't right. The conditions weren't right. If that's true, we're not late to the party. We're early. Maybe even among the very first. The galaxy and the universe will continue existing for trillions of years. Stars will keep forming. Planets will keep forming. Life will keep evolving. In 1 trillion years, the universe might be teeming with civilizations, but right now, in this cosmological moment, we're pioneers. We're among the first conscious beings to look at the stars and wonder if anyone else is out there. The answer might be, not yet, but someday. We're too late to alternatively. Maybe we're too late. Maybe we missed the party. There might have been an era billions of years ago, when the galaxy was more conducive to life and civilization. Conditions were different. Maybe stars formed in denser clusters, making interstellar travel easier. Maybe there were more heavy elements available, or better conditions for life, or something we don't understand. Civilizations arose, flourished, spread across the galaxy, and then something changed. Maybe resources became scarce. Maybe stars spread apart as the galaxy evolved. Maybe some catastrophe swept through. The great galactic civilization collapsed, broke apart, or went extinct. We're arriving at the ruins of a once vibrant cosmos. This is sometimes called the aftermath scenario. We're late to a party that's already ended. The guests have gone home. We're wandering through an empty room, wondering where everyone went. If this is true, we might find evidence. Ruins, ancient structures, dead probes, artifacts. We might discover that we're not the first civilization in the galaxy. We're the latest in a long line of civilizations that rose and fell before we even existed. It's both exciting and melancholy. Exciting because it means we'd had ancient alien history to study. Melancholy because it means we're alone now, surrounded by the ghosts of previous ages. The punctuated equilibrium model to here's another temporal explanation. Maybe civilizations come in waves. Life on Earth shows a pattern called punctuated equilibrium. Long periods of stability interrupted by rapid change. Species remain relatively unchanged for millions of years, then suddenly evolve rapidly during brief periods of environmental change or ecological opportunity. Maybe galactic civilizations follow a similar pattern. Long periods when conditions don't favor the emergence of technological civilizations, interrupted by brief windows when many civilizations arise simultaneously. These windows might be triggered by galactic events. Maybe spiral arm passages where solar systems move through different regions of the galaxy. Maybe gamma-ray bursts that sterilize regions of the galaxy and create opportunities for new life. Maybe the availability of certain resources or conditions that vary on billion-year timescales. During a favorable window, thousands of civilizations might appear within a relatively short time, say, 100 million years. They arise, communicate, interact, maybe even form a galactic community. Then the window closes. Conditions change. New civilizations stop appearing. The existing ones eventually go extinct or transcend in ways that make them invisible to us. Then the galaxy goes quiet for 1 billion years until the next favorable window. Maybe we're appearing during a quiet period. The last window was 1 billion years ago. The next won't be for another 1 billion years. We're alone not because civilizations are rare, but because we arrived at the wrong time. The life cycle of civilizations 102 to 30 to consider that. Civilizations might have natural lifespans, like organisms. Civilizations are born when a species develops technology. They go through phases: expansion, maturity, and eventually decline or transformation. The expansion phase might last a few thousand years. The civilization spreads, explores, builds, communicates. This is the phase when they'd be most visible to others. The mature phase might last much longer. The civilization becomes stable, efficient, sustainable. They might become quieter, more refined, less visible from outside. They've built what they need and settled into a stable existence. Eventually, decline or transformation. Not necessarily extinction, but change. Maybe they upload into machines. Maybe they transcend physical form. Maybe they simply become so different from their origins that they're unrecognizable as the same civilization. If most civilizations follow this life cycle, and if the visible expansion phase is brief, then at any given moment, most civilizations would be in the mature or transformed phase, quiet, stable, and invisible to our detection methods. We're hearing silence because we're looking for civilizations in their loud, expansionist youth. That most civilizations outgrow that phase relatively quickly. The synchronization problem. To finally consider the problem of synchronization. The galaxy is huge, over 100,000 light-years across. Information, even traveling at light speed, takes 100,000 years to cross the galaxy. If civilizations appear at random times and random locations, they might never overlap in ways that allow contact. Think about it like ships passing in the night on a vast ocean. Each civilization might exist for only 1,000,000 years in a specific location. Another civilization might exist 1,000,000 years earlier or later in a different location. They're both real. They both existed, but they never met because they weren't contemporaneous. Over the history of the galaxy, there might have been thousands or even millions of technological civilizations, but they were spread across billions of years and 100,000 light-years of space. The chances of any two being close enough in space and time to detect each other might be vanishingly small. We're not hearing anyone because we're all islands in space and time. Civilizations arise, exist briefly, and fade away, like candles flickering in an enormous dark room. By the time one civilization's light reaches where another will someday be, the first civilization is long gone. The universe isn't empty. It's just very, very lonely. Act 8. What we're doing about it. To SETI, the search continues too. Despite all these possibilities, despite all the reasons to think the search might be hopeless, we're still looking. And we're looking harder than ever. SETI, the search for extraterrestrial intelligence, has been going on since 1960. When astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for signals, he didn't hear anything, but he started a scientific discipline that continues today. Modern SETI is far more sophisticated than Drake's original search. We have bigger telescopes, better receivers, more advanced signal processing, and we're searching across a wider range of frequencies and using more diverse methods. The Allen Telescope Array in California is dedicated to SETI research. It can monitor multiple stars simultaneously, looking for narrowband signals that would indicate artificial origin. The Breakthrough Listen project, funded by tech billionaire Yuri Milner, is the most comprehensive SETI program ever undertaken. It's using some of the world's largest radio telescopes to survey 1,000,000 nearby stars. We're also looking for optical signals, laser pulses that an alien civilization might use for communication. Lasers can be very powerful and focused, making them potentially visible across interstellar distances. We're looking for megastructures. If an advanced civilization built a Dyson sphere or swarm to harvest stellar energy, we might be able to detect it by looking for stars with unusual infrared signatures. We're analyzing exoplanet atmospheres, looking for chemical signatures that might indicate industrial activity. Chlorofluorocarbons, for example, don't occur naturally and would be a strong indicator of technology. We've found nothing definitive yet, but we've only searched a tiny fraction of the sky at a limited range of frequencies for a limited time. The search is ongoing. The WOW signal and other mysteries. On August 15, 1977, the Big Ear radio telescope at Ohio State University detected something extraordinary. For 72 seconds, the telescope recorded a strong narrowband radio signal coming from the direction of the constellation Sagittarius. The signal was at exactly the frequency you'd expect if someone wanted to send an interstellar message, the frequency of neutral hydrogen, which any civilization with radio astronomy would know about. The signal was so strong and so unusual that astronomer Jerry Ammon wrote "wow" in the margin of the computer printout. It's been known as the wow signal ever since. We've never heard it again. Despite multiple attempts to reobserve that region of sky, the signal hasn't repeated. We don't know what it was. Maybe it was aliens. Maybe it was some natural phenomenon we don't understand. Maybe it was interference from Earth. We don't know. But it remains one of the most tantalizing possible detections of an extraterrestrial signal. There have been other mysteries over the years. Tabby's star, which showed bizarre dimming patterns that some speculated might be a megastructure, but is more likely natural, fast radio bursts from distant galaxies that we still don't fully understand. Brief signals and anomalies that get researchers excited before being explained away. None have been confirmed as alien in origin, but each reminds us that the universe is full of things we don't understand yet. Active SETI. Should we broadcast? To SETI is passive we listen. But some scientists propose active SETI, deliberately broadcasting messages to nearby stars. This is controversial. Very controversial. The argument for it: if everyone just listens and nobody broadcasts, we'll never make contact. Someone has to go first. Maybe alien civilizations are all listening too, and we just need someone to break the ice. The argument against it: broadcasting our presence might be dangerous. We don't know who's out there or what their intentions are. Announcing ourselves could be inviting disaster. It's like walking into a dark room full of strangers and shouting, "Here I am." You might meet friendly people, or you might attract the attention of someone dangerous. Stephen Hawking was strongly opposed to active SETI. He argued that any civilization capable of reaching us across interstellar space would be vastly more advanced, and history shows that contact between less and more advanced civilizations usually ends badly for the less advanced one. Others argue that we've already revealed ourselves through a century of radio and television broadcasts, so staying quiet now is pointless. If anyone nearby is listening, they already know we're here. The debate continues. Some organizations have sent messages, the Arecibo message in 1974, messages to nearby stars in recent years, but there's no international consensus on whether this is wise or ethical. It raises interesting questions. Do we, as a species, have the right to potentially endanger everyone by broadcasting our presence? Should there be global governance of active SETI, or is the risk overblown? We don't have good answers yet. What if we make contact? Let's imagine, for a moment, that we detect an unambiguous alien signal tomorrow. A clear, artificial, information-rich message from another star. What happens next? First, verification. Scientists would need to confirm the signal is real, not a mistake or a hoax. They'd need to rule out natural sources and terrestrial interference. This would take days or weeks. Once confirmed, the news would spread rapidly. Governments would be informed. The public would learn about it. It would be the biggest news story in human history. Then we'd try to decode the message. Even if aliens want to communicate, understanding each other would be difficult. We don't share language, culture, or likely even basic concepts. How do you explain mathematics, physics, or anything else to beings who think differently than you? There would be debates about how or whether to respond. Should we send a message back? What should we say? Who decides what humanity's message should be? There would be social and political impacts. Religions would need to grapple with the existence of other intelligent beings. Philosophies would be challenged. People would argue about what it means for humanity's place in the universe. There would be economic impacts too. Resources would be devoted to continued communication and research. New technologies might be developed. Maybe we'd learn things from the aliens that advance our science. Or maybe the message would be something we don't want to hear, a warning, a threat, or just information that's disturbing in ways we can't predict. Contact would change everything. We'd know we're not alone. That alone would fundamentally alter human civilization. Preparing for contact, given that contact might happen someday. Some scientists and organizations are trying to prepare. The SETI Post-Detection Task Group is developing protocols for what to do. If we detect an alien signal, who gets informed? How do we verify the detection? What do we tell the public? Linguists and semioticians are studying how we might communicate with aliens, creating systems of mathematics and logic that don't depend on human language or culture, designing message formats that would be recognizable as information, even if the content isn't immediately comprehensible. Sociologists and psychologists are studying how people might react to contact. Would it cause panic, inspiration, Would society fragment or unite? Would religions embrace aliens or reject them? Legal scholars are thinking about the implications. Who owns rights to communicate with aliens? Can a single country or organization speak for humanity? What if aliens have different ethical systems that conflict with ours? These preparations might seem premature, given that we haven't found anyone yet. But if contact happens, we'll need to respond quickly and thoughtfully. Having frameworks in place ahead of time seems wise. It's also worth noting that contact might not be what we expect. It might not be a clear signal or a visit. It might be something subtle, biosignatures in an exoplanet's atmosphere, ancient artifacts found in our solar system, or something we don't even recognize as communication. We're preparing as best we can for an event that might happen tomorrow, in 1,000 years, or never. That the preparation itself is valuable. It makes us think about who we are, what we want to say about ourselves, and how we fit into the larger universe. Act 9. The philosophical implications to the cosmic loneliness too. Whether we're alone or not, there's a profound loneliness to our situation. If we're truly alone, if we're the only intelligent life in the galaxy, or even in the observable universe that's lonely in an obvious way, we're it. Consciousness arose once in this cosmic volume, and we're the only ones here to appreciate the beauty and complexity of the universe. But if we're not alone, if others exist but we can't reach them or communicate with them, that might be even lonelier. Imagine knowing others are out there but being unable to ever meet them, talk to them, learn from them, separated forever by distance, time, or fundamental incompatibility. This loneliness isn't just emotional, it's existential. We might be the only conscious observers in our cosmic neighborhood. When we look at the stars, we're looking at places no one else is looking from. When we discover something about physics or mathematics, we might be the first in this region of space to ever understand it. That's both terrifying and exhilarating. Terrifying because of the isolation and responsibility. Exhilarating because it means every discovery matters, every achievement is genuine. Every step forward is unprecedented. We carry the torch of consciousness alone through a vast darkness. Whether anyone else is out there carrying their own torches, we may never know. The responsibility of being alone too, if we are alone, or if we might be among very few. That creates responsibility. Consciousness might be the rarest thing in the universe. Atoms are common. Stars are common. Even planets might be common. But minds that can observe, understand, and appreciate the universe, those might be extraordinarily rare. If that's true, then humanity carries a cosmic responsibility. We're the universe's way of knowing itself. We're perhaps the only ones in our region of space who can do science, create art, develop philosophy, experience wonder. If we destroy ourselves through nuclear war, environmental collapse, or any other catastrophe, we might be extinguishing something precious and irreplaceable. Not just human civilization, but consciousness itself in this part of the universe. This thought should make us more careful, more thoughtful about the risks we take and the choices we make. Not because we're special in some cosmic sense, but because we might be rare. And rare things should be protected. It also means we have a responsibility to spread beyond Earth. Not to colonize aggressively or exploit other worlds, but to ensure that if something happens to Earth, consciousness doesn't vanish from the universe. A single planet species is fragile. An asteroid impact, a supervolcano, a global catastrophe could end everything. A multi-planet species is more robust. A multi-star species even more so. We need to think long-term. Not just about the next decade or century, but about the next million years. How do we ensure that consciousness, knowledge, and culture survive and continue to develop? This isn't about human supremacy. It's about responsibility. If we're the only ones here, or among very few, we have a duty to survive and to preserve what we've learned. The mirror of humanity to the search for alien life is also a search for ourselves. How we think about aliens reveals how we think about humanity. When we imagine aliens, we often project our own hopes and fears onto them. We imagine benevolent space brothers who will solve our problems and teach us wisdom. Or we imagine hostile invaders who want to conquer and destroy us. These fantasies say more about us than about any real aliens. The benevolent alien fantasy reflects our desire for guidance, for someone wiser to help us. It's a parent figure or a savior. We want someone to tell us we're doing okay, that we're on the right path, that everything will be fine. The hostile alien fantasy reflects our fears about ourselves. We're violent and competitive, so we assume others are too. We've exploited and destroyed other cultures and species on Earth, so we fear being on the receiving end of similar treatment. The truth about aliens, if they exist, is probably far stranger than either fantasy. They'd be truly alien, different in ways we might not comprehend. Not good or evil by our standards, just different. But our projections are still revealing. They show us what we hope for and what we fear. They show us aspects of ourselves we don't often examine. The search for alien intelligence is also a search for perspective. We want to know if our values, our way of thinking, our approach to existence is universal or local. Are there other ways to be intelligent? Other ways to build civilizations? Other ways to think about meaning and purpose? Contact with aliens might not give us technological insights or solve our problems, but it might give us perspective on ourselves, a view from outside, showing us things we can't see from within. The Fermi Paradox says, warning to let's return to a darker interpretation of the Fermi Paradox. Maybe it's a warning. If advanced civilizations should be common, but we don't see them, maybe something prevents civilizations from lasting long enough to become visible. The great filter, as we discussed earlier, might lie ahead of us, some technological or social challenge that most civilizations fail to overcome. Nuclear weapons are the obvious candidate. We've had them for less than a century, and we've already come terrifyingly close to using them in anger multiple times. Maybe most civilizations destroy themselves with weapons of mass destruction within a few centuries of developing them. Climate change is another candidate. We're altering our planet's atmosphere and climate in ways that might make it inhospitable. Maybe this is common civilizations industrialize, exploit resources without restraint, and render their planets uninhabitable. Artificial intelligence is a newer worry. If we create artificial superintelligence and it escapes our control, it might destroy us or transform things in ways that end our civilization. Maybe this is a common trap. Or maybe there are other challenges we haven't encountered yet. Technologies will develop in the future that are inherently dangerous. Social stresses that cause collapse, something we can't predict because we haven't reached that point yet. The silence of the universe might be a warning. Civilizations often don't make it much further than we have now. The next few centuries are critical. Survive them, and we might have a long future. Fail them, and we join the countless civilizations that rose and fell before reaching the stars. What we should do 137-30 given all these possibilities. What should humanity do? First, keep searching. We've only scratched the surface of possible detection methods. We need better instruments, more comprehensive searches, and more creative approaches. We might find evidence of life tomorrow or in 1,000 years, but we'll never find it if we stop looking. Second, be careful. Whether broadcasting our presence is wise remains debated, but we should at least think carefully about it. Don't assume the universe is friendly or that revealing ourselves is without risk. Third, focus on survival. Whatever the Fermi Paradox's explanation, surviving and spreading beyond Earth seems like a good idea. Not to aggressively colonize, but to ensure resilience. A multi-planet species is harder to eliminate. Fourth, develop wisdom alongside technology. Technology amplifies our capabilities, both good and bad. We need to develop our ethical and social systems to match our technological advancement. Otherwise, we risk creating powers we can't control. Fifth, preserve and transmit knowledge. We're accumulating understanding about the universe, ourselves, and how to build a civilization. This knowledge should be preserved and passed on. If we're among the first civilizations, we're laying groundwork for those who come after. Finally, appreciate the mystery. The Fermi Paradox is one of the deepest questions in science. We might never fully answer it, but asking it makes us think about profound issues. Life's nature, intelligence's rarity, technology's risks, and our place in the cosmos. Whether we're alone or not, whether we ever find anyone else or not, the search itself is valuable. It makes us look outward, think deeply, and grapple with questions that matter. Final act, conclusion to where we stand today. So where does all this leave us? We've explored dozens of possible explanations for the Fermi Paradox. Each has strengths and weaknesses. Each seems plausible in some ways and problematic in others. The truth is, we don't know why the universe is silent. We might figure it out tomorrow. We might figure it out in 1,000 years. We might never figure it out. But we do know some things. We know that planets are common. Most stars have them. Many are Earth-sized and in the habitable zone. The raw ingredients for life are everywhere: water, organic molecules, energy sources. We know that life appeared relatively quickly on Earth, suggesting it's not impossibly difficult, but we don't know if Earth's path from simple to complex life is common or rare. We know that intelligence evolved here, but we don't know if it's likely or a fluke. We know that we've survived as a technological civilization for less than a century, and we've nearly destroyed ourselves several times already. We know that interstellar travel and communication face enormous practical barriers. The speed of light is slow on cosmic scales. Distances are vast. The energy requirements are enormous. We know that advanced civilizations might be very different from us. They might not think like we do, communicate like we do, or value what we value. And we know that the universe is vast. Hundreds of billions of galaxies, each with hundreds of billions of stars. Even if intelligent life is rare, the universe is large enough that we might not be alone. But the silence remains. The question remains. Where is everybody? Personal reflections. I want to share something personal. When I think about the Fermi Paradox, I find myself feeling many contradictory emotions. There's wonder at the vastness of the question. This isn't just astronomy or biology. It touches on everything: physics, chemistry, evolution, sociology, philosophy, our place in existence. There's humility knowing we might never know the answer. We're limited beings with limited knowledge, trying to understand something cosmic in scale. There's fear at some of the darker possibilities, that we're approaching a great filter, that the universe is dangerous in ways we don't understand, that silence might be wisdom and broadcasting might be suicide. There's loneliness at the possibility we might be alone or eternally separated from others by distance and time. But there's also hope that we'll find evidence of life, even if it's just microbes on Mars or organic molecules in exoplanet atmospheres. Hope that we will figure out how to survive our technological adolescence and become a mature civilization. Hope that the universe is full of wonders we haven't discovered yet. And there's excitement. We're living in an amazing time. We're discovering thousands of exoplanets. We're searching for biosignatures and technosignatures with unprecedented sophistication. We're taking the first steps toward becoming a spacefaring species ourselves. The Fermi Paradox isn't just an academic question. It's deeply personal. It's about whether we're alone and what that means for our future and our meaning. The question remains 146 to 70 years after Enrico Fermi asked, "Where is everybody?" At that lunch table in Los Alamos, we still don't have a good answer. Maybe we're early. Maybe we're rare. Maybe the others are hiding. Maybe they transcended. Maybe they destroyed themselves. Maybe they're there but we can't see them yet. Each possibility tells a different story about the universe and our place in it. Each has profound implications for how we should think about our future. The search continues. Radio telescopes scan the skies. Spacecraft explore our solar system. Scientists analyze exoplanet data. The search for life beyond Earth is one of humanity's grandest endeavors. And maybe someday, we'll get an answer. A signal from the stars. Microbes under the ice of Europa. Fossil evidence of ancient life on Mars. Atmospheric signatures of industrial activity on an exoplanet. Or maybe we'll never find anyone. Maybe the search will go on for centuries or millennia. Always hoping, never finding, slowly accumulating evidence that we might be alone. Either answer would be profound. Either would change how we see ourselves and our place in the cosmos. The universe is vast and ancient. It's been around for 13.8 billion years. It will continue for trillions more. We've been searching for less than a century. We've barely started. The silence might break tomorrow, or it might continue forever. We don't know. We can't know. All we can do is keep looking, keep wondering, and keep asking. Where is everybody? Final thoughts to if you've made it this far. Thank you. Thank you for thinking about these deep questions with me. Thank you for grappling with the mystery and the uncertainty. The Fermi Paradox matters. It's not just about aliens. It's about understanding who we are, where we come from, where we're going, and whether we're alone on that journey. I don't have answers. Nobody does. But I think asking the questions is valuable. Wrestling with possibilities, considering different scenarios, thinking about implications, this is how we grow and learn. Here's what I believe. Whether we're alone or not, we have a responsibility to survive, to learn, to preserve knowledge, and to reach for the stars. Not because we're special or chosen, but because we might be the only ones in our region of space carrying the torch of consciousness and curiosity. And that torch is precious. It might be common in the universe, or it might be incredibly rare. Either way, it's worth protecting, so keep looking up. Keep wondering, keep asking questions. Whether there's anyone out there to answer or not, the search itself makes us better, more humble, more curious, more aware of the vastness and beauty of the universe we're part of. The silence might be loneliness, or it might be an opportunity to be the first, to explore, to learn, to create meaning in a universe that doesn't provide it automatically. Where is everybody? We don't know. But we're still here. We're still looking. We're still asking. And maybe, someday, someone will answer. Thank you for joining me on this journey through the greatest mystery in science. Keep wondering, keep searching, keep being amazed by the universe, and remember, whether we're alone or not, we're part of something vast and ancient and beautiful. And that's enough. And total runtime, 152 minutes, 2 hours 32 minutes. Final word count, 18,300 words. Optimized for voice narration. No mathematical formula structure. 9 knacks covering all major Fermi Paradox explanations. Tone, accessible, engaging, thought-provoking. Extended exploration section. Bonus content, the psychology of belief 2. Let's talk about something that doesn't get discussed enough in scientific circles. Why do we want to believe aliens exist? This isn't a trivial question. To search for extraterrestrial life is expensive, time-consuming, and has produced no definitive results in over 60 years. Yet public fascination remains intense, and scientific funding continues. Why? Part of it is simple curiosity. Humans are naturally curious about the unknown. The possibility of alien life is one of the greatest unknowns imaginable. It speaks to our deepest questions about existence and our place in the universe. But there's more to it than intellectual curiosity. Many people find comfort in the idea that we're not alone. The universe is vast and cold. The distances between stars are incomprehensible. The timescales of cosmic evolution dwarf human lifespans. In this context, consciousness seems fragile and temporary. If aliens exist, if other minds are out there looking at the stars just like we do, then consciousness isn't a cosmic accident. It's a feature of the universe, something that emerges naturally given the right conditions. We're not a fluke. We're part of a pattern. This is comforting. It makes our existence seem less random, less meaningless. If intelligence evolved elsewhere, then the processes that created us are reliable and repeatable. We're not alone in being conscious observers of reality. There's also a desire for wisdom from above. Many people imagine that alien civilizations, especially ones millions of years older than ours, would be wise and benevolent. They'd have solved the problems we struggle with: war, poverty, environmental destruction, social conflict. This fantasy is essentially religious. Aliens become angels or gods, beings from above who will descend to teach us and save us from ourselves. It's the same psychological need that creates religious belief systems, just projected onto a scientific framework. The reality is probably different. Aliens, if they exist, would be products of evolution just like us. Evolution doesn't optimize for wisdom or benevolence. It optimizes for survival and reproduction. Alien psychology might be as flawed and contradictory as ours, just in different ways. They might be violent, greedy, short-sighted, or rational. They might have their own internal conflicts and problems. They might not have any wisdom to share that would help us. Or they might be so different from us that their wisdom is incomprehensible or irrelevant to our situation. What works for silicon-based hive minds living in ammonia oceans might not translate to carbon-based individuals living on rocky planets. Understanding why we want aliens to exist helps us think more clearly about the actual search. We need to separate our hopes and fears from the evidence. The universe doesn't care what we want. It is what it is. Historical perspectives to the Fermi Paradox is relatively new, but humans have been wondering about life beyond Earth for millennia. Ancient Greek philosophers debated whether other worlds existed. Epicurus, in the 3rd century BC, argued that in an infinite universe, there must be infinite worlds, many inhabited. In the Middle Ages, the Catholic Church generally opposed the idea of life on other worlds. Earth and humanity were special, created by God, and the center of everything. The idea of alien civilizations challenged this worldview, but by the Renaissance, attitudes were shifting. Giordano Bruno, in the 16th century, proposed that stars were distant suns with their own planets, some inhabited. The Church burned him at the stake for this and other heresies. In the 19th century, astronomers thought they saw canals on Mars. These were optical illusions caused by the limits of telescopes and human pattern recognition. But at the time, many believed Mars was inhabited by an advanced civilization. Percival Lowell, a wealthy astronomer, was convinced that the Martian canals were irrigation works built by a dying civilization, trying to bring water from the polar caps to the equatorial deserts. He wrote books about it. The public was fascinated. When better telescopes revealed that the canals didn't exist, the Mars civilization fantasy died, but the desire to find life elsewhere remained. In the 1930s and 40s, before we had radio telescopes, some scientists proposed that aliens might signal us using giant mirrors to reflect sunlight in patterns, or by building enormous structures visible from Earth, or by altering their planet's appearance in detectable ways. None of these signals were ever found. The modern SETI era began in 1960 with Frank Drake's Project Ozma. Using radio telescopes became the standard method because radio waves travel well through space and are relatively easy to generate and detect. But in 60+ years of searching, we've found nothing definitive. Some people see this as evidence that aliens don't exist or are extremely rare. Others argue we've barely started searching and need to keep looking. What's interesting is how our expectations have changed over time. Early SETI researchers were often optimistic. They thought we'd find signals relatively quickly. The universe seemed so vast, stars so numerous, that intelligent life must be common. The decades of silence have made many researchers more cautious. Maybe life is rare. Maybe intelligence is rare. Maybe technological civilizations don't last long. Maybe interstellar communication is harder than we thought. The Fermi Paradox has gone from a curious puzzle to a genuine mystery that challenges our understanding of biology, evolution, technology, and cosmology. The role of science fiction to science fiction has shaped how we think about aliens, often in ways that don't help the scientific search. Star Trek presents aliens as basically humans with different-looking faces. They speak English or have universal translators that work perfectly. They have similar emotions, motivations, and values. Conflicts with aliens are essentially intercultural human conflicts with makeup. This is understandable from a storytelling perspective. Writers need audiences to relate to alien characters. Making aliens truly alien would make them incomprehensible and difficult to write compelling stories about. But it creates unrealistic expectations. Real aliens would be products of completely different evolutionary histories. Their biology, psychology, and culture would be shaped by environments and selection pressures nothing like Earth's. They might not have emotions recognizable as such. They might not have individual identities the way we do. They might not communicate through sound or have anything like language. They might not value life, consciousness, or diversity the way we do. Some science fiction does try to portray genuinely alien aliens. Stanislaw Lem's Solaris features an ocean planet with a planetary consciousness that humans can understand. The aliens in Ted Chiang's Story of Your Life perceive time differently in humans, seeing past and future simultaneously. These stories are harder to write and harder for audiences to engage with, but they're probably closer to what real aliens would be like, different in fundamental ways, not just superficial details. Science fiction has also influenced public fears about aliens. Independence Day, War of the Worlds, and countless other stories depict alien invasions. The trope is so common that many people's first thought about aliens is that they might attack us. This might be unfounded. Why would aliens want Earth? The resources here, water, metals, organic molecules, are available throughout the universe. Why travel light years to take them from an inhabited planet when you could mine asteroids or lifeless worlds? If aliens wanted living space, terraforming lifeless planets would probably be easier than conquering inhabited ones. If they wanted slaves or biological resources, genetic engineering or synthetic biology would be more practical than interstellar conquest. The invasion scenario makes emotional sense to humans because we have a history of conquest and colonization. The projecting human history onto hypothetical aliens might be a mistake. Of course, we can't rule out hostile aliens entirely. Maybe some civilizations are aggressive and expansionist. Maybe they see other intelligent species as threats or competitors. Maybe their psychology is genuinely alien and their motivations incomprehensible to us. But the automatic assumption that aliens would be hostile is probably more about human fears. Then about realistic alien behavior. Biosignatures versus technosignatures. To the search for alien life has two main branches: biosignatures and technosignatures. Biosignatures are signs of life, any life, not necessarily intelligent. Things like oxygen in an exoplanet's atmosphere, methane with oxygen, which don't coexist naturally for long, or patterns of chemicals that suggest biological processes. We're starting to develop the technology to detect these. The James Webb Space Telescope can analyze exoplanet atmospheres. Future telescopes will be even more capable. If we find biosignatures, it would be revolutionary. It would prove life exists elsewhere. Even if that life is just microbes, it would tell us that the chemical pathways from non-life to life are not incredibly rare or difficult. But biosignatures wouldn't tell us about intelligence. A planet could be covered in microbes or even complex life like plants and animals, without ever developing tool using, technology building, radio transmitting civilizations. Technosignatures are signs specifically of technology and intelligence. Radio signals, laser pulses, megastructures, atmospheric pollution from industry, city lights, heat signatures from energy use, or anything else that wouldn't occur naturally. Finding technosignatures would be even more revolutionary. It would prove not just that life exists, but that intelligence and technology can evolve elsewhere. It would give us partners for communication, even if that communication is slow and difficult. But technosignatures are harder to detect. They require civilizations to be active and visible at the exact time we're looking. They require technology that produces detectable signals, and they require that we're looking in the right places with the right methods. Most current searches focus on technosignatures because that's what SETI is designed to find. But as our ability to study exoplanet atmospheres improves, biosignature searches are becoming more prominent. Realistically, we're more likely to find biosignatures first. Simple life might be common even if intelligence is rare. And biosignatures are persistent and oxygen atmosphere lasts for geological timescales. Technosignatures might be brief. A civilization might only broadcast radio for a few centuries. If we find biosignatures of no technosignatures, that would suggest life is common but intelligence is rare. This would be a partial answer to the Fermi Paradox. There's plenty of life out there, just not many technological civilizations. If we find neither, that would suggest either we're not looking correctly, or life itself is rare, or we're alone. Each possibility has profound implications. The Anthropic Principle Revisited. Let's dive deeper into the Anthropic Principle, because it's both important and often misunderstood. The weak Anthropic Principle is straightforward. We observe the universe from a perspective that allows observation. If the universe couldn't support life, we wouldn't be here to observe it. This is obviously true, but doesn't explain much. The strong Anthropic Principle is more controversial. The universe must have properties that allow consciousness to develop, because conscious observers must exist. This borders on teleology, the idea that the universe has purpose or directionality. Applied to the Fermi Paradox, the Anthropic Principle suggests we shouldn't be surprised if intelligent life appears rare. When we look around, we exist, so clearly intelligence can evolve. But our existence doesn't tell us anything about how common intelligence is elsewhere. There's a cognitive bias called the observer selection effect that's relevant here. We can only observe a universe in which we exist. If there are rare prerequisites for intelligence to evolve, we necessarily find ourselves in a universe where those prerequisites were met. This means we can't use our own existence as evidence that intelligence is common. We'd exist whether intelligence is common or rare. Our existence only tells us it's possible, not probable. Imagine a lottery where only winners are aware they played. From a winner's perspective, winning seems easy after all. They won. But this is selection bias. The thousands of people who lost and aren't aware of it don't factor into the winner's assessment. We're winners of the cosmic lottery. We evolved intelligence, though we don't know how many tickets were sold, how many planets had chances for intelligence to evolve. If trillions of planets try and only one succeeds, we'd still be here thinking we exist. So it must not be that hard. This is why we can't reason about intelligence's rarity just from our existence. We need to actually look for others and see what we find. If we search thoroughly and find nothing, that's evidence for rarity. But finding ourselves doesn't tell us much. The anthropic principle also relates to the great filter. If the filter is ahead of us, we should expect to be relatively early in our technological development, because civilizations that get much further typically encounter the filter and if we were 1,000,000 years into our technological phase, that would be evidence against a filter being common ahead of us. The fact that we're less than a century into radio technology and a few decades into space travel is consistent with, though doesn't prove a filter ahead. This is one reason some researchers are nervous about our future. Our relative youth as a technological civilization might not be coincidence. It might be selection effect. We're necessarily young because most civilizations don't get much older. The Drake equation revisited to no discussion of the Fermi Paradox is complete without the Drake equation. Even though I've avoided mathematical formulas until now, the Drake equation isn't really an equation in the mathematical sense. It's more a framework for thinking about the factors that determine how many communicating civilizations exist in our galaxy. It multiplies together several terms: the rate of star formation, the fraction of stars with planets, the number of planets per star system. In the habitable zone, the fraction of habitable planets. Where life develops, the fraction of life-bearing planets. Where intelligence evolves, the fraction of intelligent species that develop detectable technology. The length of time such civilizations remain detectable. Plug in values for all these factors, and you get an estimate of how many detectable civilizations exist right now. The problem is we don't know most of these values. We know the star formation rate pretty well. We're getting good at determining how many stars have planets, and how many planets are in habitable zones. But from there, it's educated guesses at best. How often does life develop on habitable planets? We have one example: Earth. Is that typical or unusual? We don't know. How often does life become intelligent? Again, one example. And that took billions of years. Is intelligence an inevitable result of evolution given enough time, or a rare accident? How often does intelligence develop technology that's detectable across interstellar space? We've done it, but we might stop being detectable soon as we shift to quieter technologies. How long do technological civilizations last? This is completely unknown. We've lasted less than a century so far. Some might last millions of years. Others might destroy themselves quickly. The Drake equation is useful as a thinking tool. It breaks the big question, how many civilizations exist, into smaller questions we can think about systematically, but it doesn't give us answers. Different assumptions about the unknown factors lead to wildly different results. Optimistic values suggest thousands of civilizations in our galaxy right now. Pessimistic values suggest we might be alone. Carl Sagan, one of the most famous SETI advocates, was optimistic. He thought life and intelligence were common and that millions of civilizations might exist. Others are far more pessimistic. Some scientists think we might be the only technological civilization in the observable universe. The Drake equation shows why the Fermi Paradox is so puzzling. If you plug in even moderately optimistic values, life develops on 1% of habitable planets. Intelligence evolves on 1% of life-bearing planets, etc. You still get predictions of many civilizations, yet we see no one. Either our optimistic assumptions are wrong, or something is preventing us from detecting civilizations that exist. What happens if we find nothing? Let's consider a scenario that's becoming increasingly plausible. What if we search for centuries and find nothing? We might develop the technology to thoroughly search the galaxy for technosignatures. Advanced telescopes, eye-driven signal processing, decades or centuries of observation, and we find nothing. No signals, no megastructures, no signs of industrial chemicals in exoplanet atmospheres, no alien probes in our solar system. We also might develop the technology to study thousands or millions of exoplanets for biosignatures, and find none. No oxygen methane atmospheres, no chlorophyll signatures, no signs of life anywhere we look. What would that mean? It could mean we're alone. Life emerged once in the observable universe. Here on Earth, intelligence evolved once, technological civilization developed once. We're it. This would be profound. It would mean that in a universe of 2 trillion galaxies, each with hundreds of billions of stars, consciousness appeared here and nowhere else we can detect. The implications would be enormous. We'd be the universe's only witnesses, the only minds capable of understanding physical laws, creating art, developing philosophy, experiencing love and beauty and wonder. That would make us incredibly precious. The destruction of Earth wouldn't just be a local tragedy. It would be the extinguishing of consciousness from the observable universe. The end of the universe's ability to know itself. Alternatively, finding nothing could mean we're looking wrong. Maybe life and intelligence are common, but not detectable with our methods. Maybe civilizations exist but use communication technologies we haven't imagined. Maybe they're all in hibernation or simulation or have transcended in ways that make them invisible. Or it could mean we're early. The universe is young. Most stars haven't formed yet. Most planets haven't had time for intelligence to evolve. We're the first, but eventually others will follow. Or it could mean the Great Filter is ahead and very effective. Civilizations arise, but don't last. The galaxy is full of dead planets where intelligence emerged briefly and then vanished. We wouldn't be able to tell which explanation is correct just from finding nothing. We'd still be stuck with uncertainty. But there's something important to consider. Finding nothing doesn't mean we should stop looking. Even if we search for centuries and find nothing, there's always the possibility that we will find something tomorrow. The next star we observe might have a signal. The next exoplanet might have biosignatures. The next asteroid we study might be an alien probe. The search isn't binary success or failure. It's a continuous process of expanding our knowledge and capabilities. Even if we never find aliens, we learn about planets, atmospheres, stellar evolution, and how life develops. And there's always hope. Just because we haven't found anyone yet doesn't mean no one is there. Final word count: 18,200 words. Total runtime: 187 minutes. 3 hours 7 minutes. Can be edited to 152 minutes. By removing sections ready for voice narration. No mathematical formulas. Structure: 9 main acts plus extended exploration. Practical steps forward to. So what concrete steps should we take in the search for alien life? First, improve our instruments. The next generation of telescopes is already in development. The extremely large telescope in Chile will have a mirror 39 meters across. The square kilometer array will have unprecedented radio sensitivity. These instruments will let us search more stars, detect fainter signals, and analyze exoplanet atmospheres in greater detail than ever before. We should fund these projects generously. The search for life beyond Earth is one of humanity's most important scientific endeavors. The potential payoff knowing whether we're alone justifies significant investment. Second, expand the search parameters. We focus primarily on radio wavelengths because that's what we can detect easily. But advanced civilizations might use other methods. Optical lasers can carry more information than radio over interstellar distances. Neutrinos could carry messages that pass through matter effortlessly. Gravitational waves might be manipulated for communication. We should develop detectors for these alternative communication methods. We should also look for things we haven't thought of yet. Creative, unconventional thinking might reveal new ways to search. Third, study our own solar system thoroughly. Mars might have had life in the past when it had liquid water on its surface. Europa and Enceladus have subsurface oceans that might harbor life right now. Titan has complex organic chemistry in its methane lakes. Venus, despite its hellish surface, might have life in its cloud layers where conditions are more moderate. We should send sophisticated missions to these locations, drill through Europa's ice to reach the ocean, collect samples from Enceladus's water plumes, study Mars's ancient lake beds in detail. These missions are challenging but achievable with current or near-future technology. Finding life in our solar system, even simple microbial life, would be revolutionary. It would prove life can arise in diverse environments. It would suggest life is common throughout the universe. Fourth, international cooperation. The search for alien life should be a global effort, not competing national projects. We should share data, coordinate observations, and pool resources. An alien signal detected by one country's instruments is humanity's discovery, not just that country's. We should also develop international protocols for what to do if contact occurs. Who speaks for Earth? What do we say? How do we respond? These questions should be decided collectively, not by individual researchers or governments. Fifth, public engagement. The search for life benefits when the public understands and supports it. We should communicate what we're doing, why it matters, and what we're learning. Even negative result stars we've searched that showed no signals contribute to knowledge. Citizen science projects let the public participate directly. Projects like SETI at Home, where people donate spare computer processing power, or Planet Hunters, where volunteers help identify exoplanets, make the search a collective human endeavor. This engagement serves another purpose. It reminds us why we're searching, not just for scientific discovery, but because the question, "Are we alone?" is fundamentally human. Everyone can relate to it. Everyone has wondered about it. If contact happens to let's do a thought experiment. Imagine that tomorrow, a radio telescope detects an unambiguous artificial signal from a star 40 light-years away. The signal is clearly structured, mathematical, information-rich. It's not natural. It's not terrestrial interference. After months of verification, the scientific community agrees. It's an alien message. What happens?